coming towards the ground, coming towards you. You're going to position yourself, move yourself. You're going to articulate, whatever you need to articulate, both limbs. In order to position yourself, open up your hand and actually grasp it. Right? And grasp it so that it actually doesn't fall off. That's a lot of processing that we're talking about. Right? And all of that happens in an instance. You don't really think about it. It's just happening. Now, if you have to actually recreate this, right, for an artificial system, think of all the calculations that one would have to do. What would be your actual algorithm that you would have to write? How many lines of code do you think that will amount to? A fair amount, right? A fair amount. To the extent that, think of it, 15 years ago, we couldn't even do this on a computer, on a desktop computer. Yeah, nowadays, you can calculate all of these things. But 15 years ago, no. You could not. So a lot of processing is going on, and it's our job to come up with an understanding of what is involved in each of these things, break it down into small problems, small things that we can actually compute and write algorithms about, piece them together in order to recreate what we do without even thinking about it. You don't even consciously realize it. I ask you to walk out this door. How many of you think would actually bang, on the sides of the door? Anyone? No. Right? Think of what it takes to do that. That's not easy, actually, for a robot to do. Right? Back in the early 90s, right, I spent 3 years working on a vision system just to get a robot to walk through the door without hitting the sides. It took me 3 years of work just to make that happen. Trust me, it took a long time, and there are so many things that you do not realize. Right? So, all of these things, is what we have to think about. You have to think of things that you normally do not think about. Right? Those are subconscious actions, processing tasks for you. You have to start thinking of them. That's really what image processing is about. Right? Image processing, and that's, again, I sort of say the same thing again that I said last week, which is there's a certain amount of creativity that is required in image processing. Because it requires us to think of what your brain is doing, right? Now, there is no answer, or at least there is no known correct answer, right? It's your interpretation of what you think is happening, right? And you're going to try to recreate that, and as a result, you're going to come up with your version of what's happening, and that's going to be your algorithm. It's going to give you a certain kind of results for images that you process, right? And that's what makes image processing fun and interesting, because every time someone thinks of it, it's their interpretation, their creativity into it, gives you interesting results sometimes not, right? But that's what we are here to find out, and that's what makes it fun, okay? All right, now, things that we are not very good at, okay? Visual sensing for us is relative. Our visual sensing system is not absolute. Okay? Can I tell you, how far am I sitting from him? Yeah, maybe I can guesstimate, right? Maybe 10, 11 feet. Maybe I'm wrong, I don't know. Right? I can't really tell you exact measurements. What I can tell you is he is closer to me than the person behind him. So I know relative things. Okay? Now, of course, relative things also can be misleading for us. Okay? So here's a very simple example of an optical illusion. This is something called the Mueller-Lyer illusion. Okay? You have two lines, right? Which one do you think is longer? Right. What is it? The illusion is the giveaway, I guess? So obviously we have both the same length. So is that your vision talking or is that your brain talking? Does anyone's eyesight tell them that they are the same? No. Right? The blue should be longer, I hope, than the red. Why do you think that is? That's right. So if I take away the ends of the lines, all of a sudden they'll look the same. The reason one looks longer than the other is because of the fact that when you put these corners, the bindings around the line that are at an acute angle to the line, it makes it appear compact. And the compactness makes you think that this must be smaller than the other one, shorter than the other one. So your vision system is actually seeing it, but your brain is providing it feedback, saying that, well, you know, because of the contrast around it, the way it appears, it has to be shorter. Right? And as a result, that's what we believe. Obviously, the raw signal being projected is not so. It's a feedback from the brain that makes it happen so. Okay? Here's another example. You find a black dot in there. Right? So there is no black dot in there, right? But obviously you see it moving around everywhere, right? You cannot quite focus onto it. So the vision system is actually dynamic, right? It looks at contrast changes and is expecting certain contrast changes to continue in space. Okay? Now, you have essentially a shading, right? You have black and then gray stripes, and you have a white dot in the center. Right? Now, it cannot quite make out whether the transition is exactly always that. All it is looking for is the repetition to happen. Right? And every time you try to focus in to something, it's expecting that repetition to keep changing, and your eye is in a constant mode of saccade. Right? Our eyes are never fixated. Right? Our eyes are constantly moving around. It's continuously sampling in different spaces all the time. And as a result, it can never fixate on a single dot. It just expects to see this contrast. It'll always keep moving. Again, your brain also provides a lot of feedback in terms of what it sees. Okay? And again, this is an example of the dynamic nature of the eye. If I ask you what this is, right, depending on where you focus, either you should see a goblet or you should see two faces. Once you realize that, intermittently you'll keep shifting between the two. That's again dependent on where your eye actually saccades at any given time. Right? Now in this particular case, you know, the dynamic content in this particular image is not as great as the one that we had before. Right? The variations are not as large. And as a result, the transition should be much slower. Right? You should be able to actually see the object for a little while before it might switch. Here's another example. You see a lot of lines in between the checkered patterns. Right? And each of the line might be bending in a different way. Of course, the reality is that they're all parallel lines. None of them are bending. Okay? The only reason you see them bending is based on how much of an offset there is between the blocks, between any two rows. Okay? If I change the offset in a specific order, right, make it shorter or longer, the line will bend in a particular direction. Again, this is part of illusion. It's not reality. Again, it's a matter of seeing specific contrast variations occur in the scene. So the human vision system is very, very sensitive to contrast changes. We are not very sensitive to constants. We are sensitive to changes. In fact, would it surprise you if I told you that if you had the ability to put actually a probe into your visual cortex and recreate this scene, that the only thing I would